Good morning, friends. So, in the last lectures, we started brakes and we studied what are the different types of the brakes, so that is mechanical brakes and hydraulic and pneumatic brakes, and third type of the brake is the electric brakes. So, as our subject point of view, so we are interested in design of the mechanical brakes. So, in design of the mechanical brakes, so the types of the brake is block brake. Next, the internal expanding brake, external expanding brake, band brake and disc brake. So, as per the considerations of the directions above the force which is to be applied, radial brakes and axial brakes. So, axial brakes is the example of the axial brake is the this type of the brakes, and other types of the brakes means that is the block brake, internal expanding brake, external expanding brake, and this is band brake. These are the types of the radial type of the brakes. So, that's why today I am we are studying what are the different types of the energy that is to be absorbed, that is we studied in the last lectures. So, that is kinetic energy, or that may be potential energy, or maybe so combinations of the kinetic energy and potential energy. So, that is why for your basic concept clears, today I take one of the problems related with the design above the brakes, that is above the car or for the vehicles. So, according to that, so what are the different types of the energy that is to be absorbed, and that we will consider means mass above the cars, and means kinetic energy above the car, after that kinetic energy above the four wheels, and kinetic energy above the transmissions, gearbox, and after that so these three energy that is to be absorbed for the applying above the brake. So, that is why we will see first problems related with the design above the brakes for the car. So, after that we can start design above the block brake. So, that is why please note down problems. A four-wheel automobile car, a four-wheel automobile car has a total mass of 1000 kg. The moment of inertia, of each wheel about a transverse axis, through its center of gravity. Its center of gravity is 0.5 kg meter square. So, this is mass of moment of inertia. The rolling radius of the wheel is radius of the wheel is 0.35 meter. The rotating and reciprocating parts of the engine, the rotating and reciprocating
parts of engine and the transmission system and the transmission system are equivalent to a moment of inertia to a moment of inertia of 2.5 kg meter square, which rotates at 5 times the road wheel speed. The car is traveling at a speed of 1,100 kilometer per hour on a plain road. When the brakes are applied, the car deaccelerates at 0.5, and this is G is the gravitational force. There are 4 brakes on all 4 wheels. Calculate the energy absorbed by each brake. And second, the torque capacity of each brake. So here 3 types of the energy. One is the car energy, and next is the kinetic energy of the wheels, and third energy is the kinetic energy of the transmissions, and up to that some of the energies. So that's why we'll start. So because we require more space. Solution. First is the kinetic energy of the car. So that's why here's V1 equal to, and this is 100 kilometer per hours. So this is 100 kilometer per hours. So that's why 100 multiplied by 1000 divided by, so this is for convergence hours to second, multiplied by 100 divided by 3600, this is equal to 27.77 meter per second. So first energy is the kinetic energy of the car. So that is equal to, so this is first 1 by 2 m v1 squares v2 square. So this mass of the car, this is given 100 kg. So 100 kg, so that's why, sorry, 1000 kg, v1 equal to 27.77 squares, and this is 0 square multiplied by 500. So this is 385802 joule. Next, second energy. So this is first. So second, kinetic energy of the wheels. So for the kinetic energy of the wheel, so we have to calculate omega 1. So omega 1 equal to relations V divided by R. R is the radius of the wheel, and this is the angular velocity of the wheels. The rolling radius of the wheel is, so this is 0.35 meter. So V equal to 27.77 divided by 0.35. 77 divided by, so this is 79.34 radian. So that's why here's 1 by 2 m k squares into omega 1 square omega 2 square. So m is the mass of the car wheel. So this mass of the car wheel, which will transfer through the center of gravity. So this is center of gravity directly given, 0.5. So this is center of gravity directly given. So that's why E2 equal to 1 by 2. This is 0.5 multiplied by 79.340. So this is E2. So this is for single wheel, multiplied by divided by 2. So this is equal to 1573 joule. So this is for single wheel. So E2 for all 4 wheels of car equal to 4 into 1573 multiplied by 4, 6295 joule. So next, now the rolling radius. Now the rotating parts of engines are the parts of third. Kinetic energy of rotating parts of engine and transmission system. So here's to a moment of inertia, So here this is given I equal to 2.5 kg meter square, and which is rotate at 5 times the radial wheel speed. So that's why this is omega 1 equal to 5 times omega 1 of car wheel. So omega 1 is 79.34 multiplied by 5, 396.7 radians. So that's why against right half into I into omega 1 square. So this is 2.5, this is given, and this is 396.7 square minus 0. Bracket square multiplied by 2.5 divided by 2. 196,713 joule. Now total energy E equal to E1 plus E2 plus E3 equal to 19673 plus 6295 plus 385,802. So this is equal to 588.81 joule. Now for so this is the total energy. One brake energy which is to be absorbed equal to divided by 4. So this is 1472 joule. Right. Now next is the so this is given deaccelerate 0.55. The braking time is given by V1 divided by R equal to 0.5 gravitational force. So that's why, or this is time, sorry. So T equal to V1 divided by 0.5 into 9.81. So V1 equal to 27.77 divided by 27.77 divided by 9.81 divided by 0.5. This is equal to 5.66 second. So theta equal to omega 1. So this is average speed multiplied by time, omega 1 square. So omega 1 equal to omega 1 79.34 2, and this is 5.66. 79.34 divided by 2, this is equal to 224.59 radians. So that's why here lastly E equal to mt into theta. So E equal to 147,202 multiplied by torque and theta equal to 224.59. So torque equal to 655 Newton meters. So this much is the torque which is to be absorbed by the brake. So this is expected answer. Right. So this is problems related with the design of the brakes, but this is only understanding purpose. So now we will see actual types of the brakes is the block brakes. So in the block brake, such type of the brakes that is used in the trains, and this is block brake. Application used in railway engine, wheel braking system, and here's and the length of arc of contact means theta equal to, this is 45 degree. So this length of the arc of contact. So this length equal to, so this is limited 45 degree. 45 degree. So in the block brakes. So here's components require lever, actuating force, pedal with spring, brake drum, and shoe materials. So during the design of the block brake, so what are the important parameters? So important parameters is to be so following important, you can say this is following important parameters is to be consider for designing of block brake. So here's first is the area of contact of braking surface. So this is very important, the area of the contact of the braking surface. So here's length of the arc of the contact multiplied by width. So that is L and width. Second bit, the friction, the coefficient of friction material. Third, the radius of a brake drum. And fourth is the pressure between, the pressure the normal pressure. You can say this is the normal pressure of braking surface. So the normal pressure, what is the normal pressure? How much is the normal pressure that is applying on the brake drum? That is to be considered. So this is the radius of the brake drum. Suppose this is the radius, and now this is pivoted end. So yes, and this is block. So this is the, or you can say this is a radius. Now L is the, this is L is the length, and it's across. This is width, and this is theta equal to here force that is to be applied. So this may be rotating clockwise or anti-clockwise. So if rotating anti-clockwise, so this is rotating anti-clockwise. So next, now last point is the amount of the heat which is absorbed by the brakes, that is to be dissipate. So that's why So this is parameter is to be considered. So this is for brake, the ability to brake, the ability of brake to dissipate heat that is equivalent to the energy absorbed. So actually these point is to be considered for the design of the brake. So means any type of the brake. So that is forgetting in the last in the introduction of the brake. Now we'll see this is the block brake. So in the block brake, so we already discussed that angle subtended. This is 45 degrees, the maximum angle subtended by the block brake. Why this is 45 degree? Due to limitations of distributions of uniform pressure, distribution. So that's why this is so length. If the length is increased, the width of the block that is to be minimized, and if the width is increased, length of the block that will decrease. So that we'll see after that. So only important points that I will here explain. This is breakdown. Now this is actuating for lever. So this is pivoted end, and this distance equal to A, and this distance is the B. So here this is the force which is to be applied, and this distance is C. This is rotating clockwise. This is block. This is lever. This is brake drum. This pivot end. So the force acting here, this force is the normal force acting or free body diagrams. Free body diagrams. This is rotating clockwise. This is R. This force P, and here's force. This is N. Here also N, and this is rotating. So that's why this is frictional force mu N, and here acting this frictional force. This is equal to mu N. This distance equal to this distance is C. This distance is A, and this distance B, and this is actuating force. P is the actuating force. So that's why, yes, due to limitations above the uniform pressure distributions, so here T is braking torque in Newton meter. R is radius of brake drum. Mu is coefficient of friction. N is normal reaction in Newton. So the dimensions of the block, the dimensions of a block can be determined by using relations equal to P into LB equal to N minus, this is N. So B is the, L is the length of block, and B is width, or you can say this is W, because B is, we are considering these dimensions is B, so that's why W is width. P is pressure between brake drum and shoe material. So that's why here's now the width of the block, that is optimum width. So optimum width for uniform distributions, that is in between 1/4 of diameter of drum. This is optimum width. And this is half of diameter of a drum. So the width, so if the width is narrow, if narrower width, if narrower is the width of block, unnecessary, the size of break will increase. Size above the break, that will increase, and if the width above the, that is great, so that will not, and if width is more, so the pressure between shoe and brake drum is not uniform. So that's why this is the, so multiple choice question may be asked. So why this is to be maintained 1/4 above the diameter of the drums, and this is the optimum width of the block equal to half diameter of the width. This is important. So try to understand this. So after that, considering the equilibrium forces, the equilibrium forces Rx equal to, this is horizontal, equal to mu n, and Ry equal to vertical forces n minus P. Here two forces. Now by taking, so this is free body diagram. So by considering considerations of free body diagram, for equilibrium moments, so we can apply now equations. So this is anti-clockwise, and this is also anti-clockwise, and this normal force clockwise. So that's why P B into P minus, this is anti-clockwise, and this n into A plus mu n into C equal to 0. Now this is B into P equal to UN, sorry, this is into C, sorry, Now P equal to actuating force equal to, so here's A minus mu C multiplied by N divided by P. So this is the common relation. So this is the common relation. So here's three case. Case first. So if A is greater than mu C, so this is indicates some of the force is required for braking. So that is the actuating force required. Actuating force is required. So that's why this is the condition in hand of operator. So operator can apply the force, and that force is the small force, because if this is A is greater than. So this is the conditions above the operator with small force is required. Next case second, if A is equal to mu C. So here's this is not this condition is not good, because this may be self-locking. So that's why here during running condition brake may be applied and energy may be grabbing. So that's why this is not this condition is not suitable, is not in hand of operator. So try to understand this. And third case, if A is less than mu C, so this is the friction material, so this is the worst condition. And never allowed, because this is self-locking. No force is required. Is in the hand of the operator. So that's why this condition is not suitable. So only this is the condition. So this is for when this is the rotating in the anti-clockwise. So here means for anti-clockwise minimum force. So this force is, so you can say conclusion, so if directions of actuating force and friction force are same, minimum actuating force is required. Now suppose these directions change. Now if directions is anti-clockwise, breakdown directions, I will change this direction. So that's why this is change. Now instead of this frictional force and this actuating force, so here's, so this is try to understand. And this is, and this is. So in this case, by applying moment equation, so in this case P into B plus, anti-clockwise, n into A minus mu n into C equal to 0. So that's why P into B, A into n plus mu n into C, or P equal to now A plus mu C into n divided by B. So in the previously case, in the previously arrangement, so this is P equal to A minus mu C and divided by B, and this is multiplied by. Now this is increased. This is increased means more actuating force is required. So that's why this condition is more suitable, because minimum force is the actuating force is to be required for the apply. So that's why the directions of the friction materials and the directions of the actuating force, that should be in the same direction. This is anti-clockwise, this is also anti-clockwise. The directions of is anti-clockwise of brake drum. So that's why anti-clockwise directions both are in the same conditions, means that is more suitable as compared to the when the actuating force and the frictional force both are in the opposite. So in the next class we will see problems related with the design of the brakes. So that's why today's topic is. Thank you.